List of the terms. You made a few of the terms? So what's the first term when you plug in 1? What? Yeah, you get ln of 2 over 1, right? What's the second term? ln of what? Huh? 3 over 2. And ln of what's next? 4/3. So you wrote these out. Do you remember what happens when you add together logarithms? Yeah, so you add these all together, right? If you added these ones together, what do you get? You get ln of what? 2 times 3 times 4 times 5 over what? 1 times 2 times 3 times 4. What happens? Oh, look what just happened there. This is the first 4 terms added together. What did we get? ln 5. This is the sum of the what? First what? First 4 terms, right? First 4 terms, right? So if I add another term on, what would it actually be? The ln of 2 times 3 times 4 times 5 times 6 over 1 times 2 times 3 times 4 times 5. What happens? What is it? ln 6. This is the sum of the first what? 5 terms. So if I wanted the sum of the first n terms, what would it be? ln of what? n plus 1. There it is. It all cancels if you just do it out, right? It's ln of n plus 1. Okay, so this is the partial sum, right? If you wanted the n terms added together, what happens to this as n goes to infinity? It blows up. So this thing diverges. Cool stuff, huh? It cancels. Like, just do it, and look, it all goes away. It all goes away. Okay, well, you just do A by making, they group it together for you. They group it together for you. So let's look. Let's look. I'm going to write out some terms, okay? You have 1, you have a half, you have what? A third, and then what? 6. Keeps going, right? If I could actually write it out. You with me so far? Let's look at these terms right here. That's the first group, right? No, sorry, excuse me. It was, what did they group? How did they group it together? Shh, hold on, one at a time. Say it. 3 and 4, yeah, it's these two, right? Okay. Do you agree that all the as you go to the right, the terms are getting smaller? Do you agree that 1/3 is greater than 1/4? So this is going to be greater than 2 times a quarter, correct? Do you agree with that? Okay, so what's the next group they gave you? 1, 5, 6, 7, 8, right? Do you agree that all of these are getting bigger if you go to the left? So a 5th is greater than a 6th, is greater than a 7th, is greater than an 8th. So do you agree that the first 3 terms are all greater than an 8th? So these 4 terms all have to be greater than what? 4 times what? An 8th. How many terms are in the next group? How many terms are there? There's 8 of them. What's the last term? So do you agree it has to be greater than that? Do you agree? What is 2 times a quarter? What's 4 times an 8th? What's this? A half. So here's the thing. You have a half, and then you have a half, and then you have a half, and then you have a half. How many terms are in this series? What have we shown you can always add? A half. So if I want another half, how many terms is it going to be? 16, right? Because it'd be 16 over 32. If I wanted another half, how far would I have to go? Another 32, and then another 64, and then another. How far can I do that for? As much as I want. So therefore, what happens to this series? It diverges as big as you want. This right here is the coolest way of showing this diverges, I think. Pretty cool. You can always build another 1/2. So what we have shown, you can always build another 1/2. That's what we've shown. Happens. So if you actually do this one out, what do you have to rewrite it as first? Do you remember? We've done this a couple times so far. What do you have to do first? It's the limit b to infinity 1 to what? Of this, yep. Instead of writing 1 over x squared, sometimes it helps us to write it as what? Yeah. Does that help you with the integration a little bit? Maybe. Maybe. So what's this going to be? Yep. It's going to be... Oh, wait. I'm doing the integral, so I don't need to. It's going to be negative what? X to the... And you're going from what? 1 to what? 1 to b. Are you with me so far? Okay, so now you just have to be careful and not mess up the negative signs. Now you just have to be careful and not mess up the negative signs. So if you do this now, you end up with the limit as b goes to infinity of what? Negative 1 over b minus what? Negative 1 over 1. What happens to this right here? That goes to 0. To what?
1.
Oh, look at that. So if you sum up everything under the curve from 1 to infinity of 1 over x squared, guess what you get? 1. Okay, so 1/5. That sound pretty good?
Yeah.
So what we're getting to here is we recircled back. I already showed you the proof of this. I pasted into the notes from a couple days ago. This was the proof of the p-series, the general proof of p-series convergence. What did we learn about this? What were the values of the exponent p for the improper integral diverges? Or when does it diverge? You remember? When does it diverge? We know this. When the absolute value of p is less than 1, right? But if p is greater than 1, what happens? It converges. We know that, right? So now we're just taking what we knew about p-series and applying it to integrals. So it doesn't really change anything. There's no different math behind it at all. Okay. In this one right here, I was working with this yesterday in the other class, and there's something missing from here. What's missing? There's no limit, right? I didn't actually give you, there's no limit listed, so my kids are like, yeah, you can do that, right? What happens if you did this? Sorry, we'll move the whole thing, sorry, one sec. What's the problem there? Why is this an improper integral all of a sudden if I put limit as a goes to 0?
Oh, because you can't have that.
You can't evaluate it, right? You're gonna run a contradiction here. So there's ways in which you can manipulate this. Like you can flip it over if you want to, right? You can flip it over and you can rewrite this one and actually do it out. So I'm gonna leave this one as an open question right now. So this was a problem because this one, the integrals that we've looked at so far, they've looked like substitution with like tan inverse squared or something. Nah, it's not. Here's the thing. Let's look at this right here. Can someone tell me what the comparison is between these two things? What's the comparison in quantity? What happens if you make the denominator bigger? It gets smaller. So do you agree with this? Yes. What can you tell me about this? This converges, right? So therefore we know that that's less than something that converges, so therefore this what? Converges. Done. Pretty cool, huh? That the crux of that is we know that that's a p-series that converges, and we know that each corresponding entry is less than. Oh man, let's see what other crazy things we can do. So we get to sand things away. This is where it gets real fun. Well, I think it's real fun, so hopefully you do too. Let's look at A right here. Let's look at A. Okay. When n gets really, really big, so the question you're going to ask yourself is, what am I trying to make it look like, Tina? And on this one right here, when n gets huge, what are the only terms that are going to matter in this fraction? It's going to look like n over n cubed, right? So as n goes to infinity, this function is going to look a lot like what? 1 over n squared, right? 1 over n squared. So let's compare the two. So if I have this, n minus 1 over n cubed plus 3, when you make the numerator smaller by subtracting 1, what happens if I changed it to this? What's the comparison here? What's the comparison? Yunji, get up. What's the comparison? Less than, right? No, she was sitting. Is that true? Is that true right there? Okay. What about this? N over n cubed. What's the relationship now? If you make the denominator small, it's going to be what? It's going to get bigger again, right? But what does this equal? 1 over what? N squared. Do you agree? We know though that this, what does this do? Converges. So we have this less than this, so therefore what does this whole thing do? What does this do? Converges. Nice. Very cool. So let's talk about B right there. Let's talk about B. Let's see what this looks like. So we want an idea about what to sand this into, right? When n gets huge, what does this thing start looking like? 3 over n. It looks like 3 over n, right? Does 3 over n converge or diverge as an infinite series? It diverges. It's 3 times the harmonic, right? So if this looks like something that diverges, we want to show that this is below or above it. We want to show it's above it, right? Because here's the thing: if something diverges and we're below it, what do we know? Nothing, right? So if this looks like something that diverges, let's show that each term is bigger than 3 over n. Well, look, 6n squared plus 1 over 2n cubed minus 1. Let's just take one away here. 6n squared over 2n cubed minus 1. What happens? We just made the numerator smaller, so what happened to the fraction? It got what? Smaller. So let's do it again. 6n squared, 2n cubed. What did we do? Did we make the fraction bigger or smaller? Smaller again. The denominator got bigger. The numerator got smaller, right? So it's smaller. 6 over 2 is 3n squared over n cubed. What do you end up with? 3 over n. So what do we know about this series right here? Yeah, what is this? Divergent, right? So therefore, what do we know about this? Diverges. Pretty cool, huh? So you're going to have building blocks like the harmonic series that you know diverges, that you can show above that, it blows up. You're going to have things that you know converge if you show below that. It's kind of cool. So there's an extrapolation of this, which comes down to this. This right here is a lot deeper. But before we study this, everybody stand up and get over into the corner before we forget. Come on. So how do you go about using this? Well, again, remember how someone said on the homework, did you have to use the integral test every time? And the answer is probably not, but maybe you did. Just because one method works doesn't mean another method might not also work. So this one, there's one method we already know, but let's use this new method. This right here, if I look at this one right here, if n gets really, really, really big, what does that look like? What does it approximate? 1 over n squared. So we're going to call this right here our an, and our bn is going to be 1 over n squared. We are going to do the limit as n goes to infinity of an over bn. Well, I'm going to write it in now, the limit as n goes to infinity of, what is it? N squared plus 6 over n to the 4th minus 2n plus 3. And what are we going to put that over? So it looks terrible, and you're like, why, Mr. Seamon, why would you ever write that on purpose? When you divide by a fraction, that's the same thing as multiplying by the inverse, the reciprocal. It's not quite the same. So you now have the limit as n goes to infinity of, what do you have here? N to the 4th plus 6n. I'm just doing the algebra out faster. Is that okay? Are we okay with that? What does that limit equal? 1. Right? Do you agree with that? It equals 1. What do we know about this right here? What is the sum of bn? Does it converge or diverge? This converges, right? Do you agree with that? So because this right here is greater than 0, what does that tell us about an? Therefore, an converges. So here's the thing. If you can find something to throw into the ring and obliterate it and come out just like equal, you up a 1 right there. It didn't blow up. It's greater than 0. Oh, look, it worked. It's really cool. But here's the thing. You have to know what to choose. So looking at end behavior is good, but let's change it up a little bit. What about that one? Ooh. Have you seen things like this before? Yeah, you've seen things like this before. What does this thing look like? You remember what this looks like? Kind of goes like this. Oh, and then it does like weird oscillations and stuff. Right? Like it gets real fast. What around zero? What does this look like? It's infinite oscillations, right? Like between -1 and 1, it's an infinite number of oscillations. Okay. So the question is, what happens if you sum all these up? The sine of 1, the sine of 1/2, the sine of 1/3, the sine of 1/4, the sine of 1/5. Is it geometric? No, it's clearly not. So the question is, if I told you to use the limit comparison test right here, right? If I told you to use the limit comparison test, you need to pick something to compare it to. It's all about what you compare it to. What might you think you should compare this to? Give me a random guess. Cosine, right? Was that right? No, but that's what the other class said. But you're like, oh, cosine and sine, it comes out to 1. You square stuff, you get an identity, you're done, right? Another guess? Sine n, right? So this is where math can sometimes be tricky because you could these are all valid guesses, but when you try them, they don't lead you anywhere. We need to pick things that we know either definitely diverge or definitely converge, right? So how about we do this? 1 over n. So let me do this. The limit as n goes to infinity of sine of 1 over n over 1 over n. That's equal to the limit as n goes to infinity of n sine. Have you ever seen this before? Does anybody know what that is? The limit as n goes to infinity of n sine 1 over n. You didn't do this in AP Calculus? Do you remember? There's a proof for it. This is just something you kind of have to know. We're not going to do this in class. Yeah, it comes out to? It's going out to 1. What do you think? What do you think? Let's say it came out to 1. You're right, it does come out to 1. So it came out to 1. What do we know about 1 over n? 1 over n divergence. What does this have to do? Basically, you can think of the only way this has the superpowers this has. The only way they can cancel each other out is if they have the same superpower. What's the same superpower? In this case, they diverge. Does that make sense? Is now 129? You are free. See you, kids. Have a great